Philosophy class, this is 1.4, classical logic, proof theoretic validity. This is uh, this is seeing what happens when you have a system of rules. Does a conclusion follow from the premises? This is different than what we did last time, semantic validity, where we were worried about if you assign true values to the premises, can the conclusion have a false value? This is more worried about just rules. You just set up a few rules, and you're not worried about true or false. Um, this is going to be a little bit more difficult than the last one, so buckle up. Here we go. Last time we saw the sigma, and we saw the little like double T, right? It looked, let's see, it looked kind of like this. Sigma that A, right? Let's see here. This time you're seeing just the one. This was for semantic validity. This is for proof theoretic validity. So a set of formulas, sigma, a set of formulas proof theoretically entail a formula A, a conclusion, right? If and only if there's a complete tree whose members consist of sigma and not A, which is closed. All right, this is like I said, this is a little more difficult, but here's basically what you're saying. You'll see what a tree is in a second. We're working actually with Tableau, and they're not the only way to do this. It's not the only way to set up a system of rules and see if what follows from what. But this is one of the ways. If you set up this system of rules, and you start with sigma, which is all your premises, right? And then not A, which is kind of like saying A is false, right? You're saying you're taking the opposite. Will that system close? And by close, you'll see what that means when we start doing it. But close means when it'll close if these will work together. In other words, can I make sigma work with a not A, with the opposite of the conclusion? And if I can, then A will not follow from sigma, right? Because I could have not A with sigma and G just fine. That's basically what we're getting at. Again, some definitions. This gentleman right here, proof theoretic consequence, and you just say that it's not a proof theoretic consequence by throwing a slash on it. We're going to be working with Tableau trees, and here's what they're going to look like. You're going to start off, let's say, sigma. You want to see if this works, right? Sigma proof theoretically entails A. You're going to start off at the root with sigma and not A, like we just said. Sigma and not A. And then you're going to see a bunch of different rules that take you, split them up and make them do all kinds of crazy things. And at each stopping point, each time you write something, you'll have a node. We'll call them nodes, these little dots right here. You won't have dots. There'll be formulas there, right? And each one of these little arrows will be a branch. A lot of times we'll just get rid of branches that go straight down. But for these, we'll draw the branches. But in any case, when it's going down, that's a branch. Or going down like that. And then when you get to the very end and you can't get any further, that's the tip, right? Sometimes the tip, at the tip, it'll close and we'll put an X, and sometimes it will be open and we'll leave it open. If you have a whole, I said when they split off like this is a branch. I should have said really, it's a whole splitting off, right? So it's from the root all the way down to the tip. That's a branch. Yeah, this looks pretty ugly, I admit. So hang with me until you actually start seeing the examples. Then it'll make a lot more sense. But here's basically what we're doing. You're going to construct an initial list. That was the sigma and not A. Remember, we want to see, does sigma entail A? So we're going to construct an initial list, which is a single branch at whose nodes occur the premises, which is all sigma, right? And the negation of the conclusion, not A, right? We're negating A right here. This is the initial list. Sometimes sigma, it says here, if any, sometimes sigma is empty. We saw that in the last one. I showed you how if you do something like P or not P, right? Those are, doesn't matter how you assign the truth values, it's always going to be true, right? Something like that would be, without a sigma, it would be just A. Then you apply the Tableau rules, which I haven't shown you yet. That's coming up. The Tableau rules will tell you how to change these guys. right? And that will cause all the branching out, all those weird looking things like that. This is N1 means note 1. So if we apply a rule to a formula, then if the formula is true in an interpretation, so are the formulas below on at least one of the branches that the rule generates. What does that mean? That means if you apply all the rules and you get all these branches, and you apply the rule and the formula is true in the interpretation, then you're going to see at least one branch that is true, right? And that'll make a lot more sense too while we continue to go. We'll say that a tableau is complete if and only if every rule that can be applied has been applied. And so you'll see the rules soon. If you apply all the rules, you can't apply any more, then this thing is completed. A branch is closed. Remember, a branch is from the root to the tip, is closed if and only if there are formulas of the form A and not A on two of its nodes. Now that doesn't mean it has to be the conclusion that has an A or a not A. All that means is some formula that is A and the same formula negated, right? So if sigma equals B, let's say I want to see B and not B. Oops, not A. B and not B. Let's say that's what sigma equals. So equals, and I wanna see if that entails A, B and not B, and here we have not A. Right. So I want to see, does this work with this? If it doesn't, then I have to have A when I have this. So then A follows from it. So one rule would be, let's say, if I have B and not B, then I get B. Therefore, I have B and I have not B. Oh, but wait, I have a B and a not B. You can't do that, right? The tableau's the branch is closed. I have a B and I have a not B, right? So let's draw a line here. I have this and I have this. So that's closed. And if it's closed, we'll just draw a little X just to let you know. Can't go any further. And the branch is open if and only if it's not closed. So if I don't get an A of two formulas, one negating the other, then that branch is open. Oh, this is the same slide. No, it's not the same slide. Oh, this tells you what the initial list is. I don't know why that's different, but there it is. All right, so here are the rules, and the rules are go off basically what something similar to what we had with the semantic validity, right? So these are rules. I'm not talking about the true or false anymore, but really these are pretty close to what we were doing. For if you have an if A then B, right? If you have this guy. Remember that was, I don't want to draw the circles because I'm a horrible artist, but remember what I was saying. What this means is you can't have A true and B also not be true, right? So then we said, well, hey, that means if B is always true, then this whole thing is true, right? Or if not A is true, then this whole thing is true. So the way this rule goes, if you see something of the form if A then B, A this thing B, then you're going to split those into two branches, the first being not A and the second being B, because this rule will be true if either one of these conditions are satisfied, right? That's more where we're getting at. We're not getting at true or false. We're saying the conditions are satisfied, then this thing works. A or B, you will split the two, because remember A or B is saying at least one of these two things. So if at least one of these two things, this will be satisfied if at least one of these two things, right? A and B, this will only be satisfied if both of these things. So A and B. And remember, like I said, you really don't need to draw these little arrows if they're going straight down. You should draw these guys just to keep yourself, to keep it a little more organized, but you won't have to draw the straight down arrows. A, if and only if B. Remember I said what this means is if you have one, then you have to have the other. If you don't have one, then you can't have the other. So that's what this does. It goes over here. A, then if you have both A and B over here. If you have not A, then you have not B. Something like that. Not A. This is kind of like in math where you have a double negative. You're saying you do not have not A. Alright, so then that means you have A. Now these are the negations of these rules up here. If you do not have if A then B, remember I said the one thing you can't have if it's if A then B, you can't have if it's if A then B, you can't have A being true without B being true. You can't have A without having B. I should get rid of the true and false because we're talking about proof theoretic. So, well, if it's not if A then B, that you do have A without having B. So A and not B. Over here we said this condition is satisfied if at least one of these conditions, at least A or B is satisfied. So here neither one is satisfied. If I don't have that, then I don't have A and I don't have B. I said A and B is only satisfied if you have both A and B. So not A and B is satisfied if you're missing A or you're missing B. And this is basically, you can see it's just the direct opposite of this. A if and only if B means if you have one, then you have to have the other. If you don't have one, then you can't have the other. So that's what you got here. You have one without having the other. Have one without having the other. Those are the rules. So what does it look like when you actually do them? Well, it looks something a little like this. Let's pretend we have an if A then B, if B then C. And we want to see, does it make this follow, if A then C? Well, so first thing we do is construct our initial list. That consists of all the premises listed out right here, if A then B, B then C, and the negation of the conclusion, not this thing. Ooh, that's supposed to be parentheses. Shoot. That looks horrendous. Let me erase that. There you are. Not if A then C. That's what we have here. So I listed them out. I have my initial list, and let's go from there. We'll use our rules. So our first rule was if you have a negation of these two, that means that you have one. You have the first one without having the second one, right? So if A then C, not if A then C, then you have A and you have not C, right? So that's the first rule. And one thing you might want to do is just check this guy right here to let yourself know, hey, I got this guy covered, right? If A then not C. And then these rules, remember, these were split them up rules. If A then B, you have this condition satisfied if you either have not A or you have B. So we'll split these guys up, not A and B. And then you have a little check there to let you know you got that set. Now you don't check these guys because these guys are like atomic, right? They're at the bottom level. You can't get any further. There are no rules to make them smaller, so you don't have to worry about did I apply a rule to that. Because remember, we have to complete this. We want it completed, and in order to make it completed, we have to apply all the rules. That's all we're worried about. These checks are just to help you remember. And then I haven't checked this one because I haven't applied the rule yet. Same rules I've applied here. I need either not B or not C. Not B or C, excuse me. And I have to apply it to both branches, right? I have to apply it both sides. Well, so then I have this set. So now what I'm going to do, I'm going to look through this and I'm going to see, is there anything here, any branches here, are there any branches here that did not close? Well, I have a not B here, I have a not A here, I have a not C. I have an A here with a not A. That means this will close and this will close, right? A and not A on both of these branches. Now, what I could have done here is I could have just closed this off here, not worried about applying it here, but I'm just doing this so that you can see. Here I have A, not C, B, and not B. So B and not B, closed. Here I have A, not C, B, and C. So I have C and not C. This is closed. So this is valid. This is proof theoretically valid. If A then B, if B then C, does entail if A then C, right? And you may wonder, but didn't you make a negation? Remember, the negation was just for this to work. I'm just looking to see if I have these two, could I have the opposite of this? If I could not have the opposite of this, then I must have this one. So let's erase that so we don't get confused. So these two do make this one follow. And if you think about it, it really makes sense. what you're saying, if A then B, if B then C, therefore if A then C. It's kind of the, what is it, transitivity, I think, property, something like that. I don't know, whatever that's called in math. Alright, let's see another one. We want to show that it's not the case that both A and B does not entail that we have not A and you have not B. This is something I actually, this is a fallacy that I showed you earlier, right? I showed you this guy. Oh, that is horrendous. I showed you this is A and B. A and B means that you're in here, right? So not A and B means you're outside of there. So you could be here, 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 but you can't be in here, right? So either B is going to be false because you're in one of these two things, or A is going to be false because you're over here. But it's not true that, or both of them would be false because you're out here, but you just can't have A and B. Well, so that shows that you don't have to be out here. It doesn't have to be the case that you're not A and not B. So this won't follow. But will it work with our little setup here? So what we got to do, remember, we got to take this, our initial list, take the premises, write them first, then take the conclusion and negate it and say, can the premises live with the opposite of the conclusion? If they can't, then you have to have the conclusion. So notice I put the parentheses around this. Remember, if I didn't, that would be not A, which would be A. But no, it's not this whole thing. So I have my parentheses around here. So let's start applying some rules. The first rule I'm going to apply is to split up the conclusion. It's not these two things. So one of them is false at least, or I'm sorry, one of them doesn't work at least. One of them is negated at least. So not A or not B, right? And then I can check this guy off. And then the next rule I'm going to apply is getting rid of these nots, right? That's a rule too. Not A equals A, so I got these guys out of the way. Now the last guy I have to worry, I can't change these any. These are base level, they're atomic. So I have to worry about this. I'm going to split that one up too. Not A or not B. Not A or not B. Well, now here I have an A and a not A, closes. Here the only thing I have is an A and a not B, so this is open. So already I could stop right now and I know that this is invalid. I'll check the other ones just for fun, but not for fun, but just for showing you, because this is not fun at all. The next one, B and not A, this one is also open. That's the only two you have. You don't have an A or a not A. That's how they close. Remember, you have to have something of this form, B not B, close. So these two are open. That shows that this, oh, I didn't mean to do that. That shows that this does not entail this over here. Alright, so that's all neat and swell, but what does that mean? If we're not talking about truth or falsity, what do we care, right? We're just going to play a game and do what, right? So what we want to do after we've shown proof theoretic validity, after we've shown that one thing follows from another, we want to then show that based on the one of the things that we saw that didn't work, we can show you the true and false all of a sudden and how it doesn't work. So what we're going to do, we're going to find an open branch of the Tableau. Back here you saw, like, this is an open branch of the Tableau, one that did not close, and we're going to give all non-negated propositional parameters a 1. Now for here I didn't actually have any propositional parameters, I used formulas, right? But let's say these were P's and Q's. I would give this one a 1 because it's not negated. This one I would give a 0 because it is negated, right? So all negated propositional parameters are 0. The result is the interpretation V of the propositional parameters. So the result is what we were doing before with the semantic validity, right? The result, I see a place where if I assigned the propositional parameters this kind of truth value, then the conclusion can have a false truth value. So let's do an example of that. This is not both P and Q, does not entail, same thing we just did, right? This is the same thing we just did. That's crazy. Okay, so not P and Q, you saw this is exactly what we just did, right? I guess let's just go through it one more time, just just to help you guys out. All right, so I take the premises, this guy right here, then I negate the conclusion, the whole conclusion, right? That should be a parentheses. So not this thing, and I want to see, can this guy live with the opposite of this thing? And if it can't, then it must entail this thing, right? So not P and Q, not P and not Q. Alright, the first thing I do is I'm going to split these guys up into not P and not Q. That's a rule that I'm using, right? And then I can check this guy off, and then I want to get these guys out of the way, the not P and the not Q, and then I'm left with this, and that is splitting out to not P, not Q, or not P, not Q. These two close on the outsides. These two remain open. So now what I can do, I take an open branch, let's say this one, and I see all the propositional parameters. This one is P, this one is not Q. The ones that are not negated have a 1 value. The ones that are negated have a 0 value, right? So Q has a 0 value. And so the counter model will look like this. The truth value of P is 1, and the truth value of Q is 0. I could also do a counter model for this guy right here, right? I could make another another counter model where the truth value of Q is 1 and the truth value of P is 0. The reason you can do that is there's more than one way for this to be false. There's more than one way to mess this up, right? You can assign truth values to P and Q in more than one way and have this thing set up be wrong. So that's what a counter model is. And that is the end of proof theoretic validity.